Hey everyone, and welcome to this module. This module is one of the most important modules in tensor algebra, and it's about tensor transformation and transformation rules. So, in the first part, we review the tensor transformation. We Up until now, we have discussed the transformation rules of a vector in a second-order tensor, but in this session, we also find the transformation rule for higher order tensors like the third, fourth order tensors. And then we bring the transformation rules, such as the addition, multiplication, and the quotient rule. So let's get started by the transformation rule. Tensor transformation. So, all right. So up until now, we said that we can write, vectors, tensors, and even the scalars and a form of tensors. So if you start from the zeroth order tensor or a scalar, we denote it by, for example, alpha. And if we transform this alpha into from a prime from an unprimed coordinate system to a prime coordinate system, it remains as it is. So alpha prime is equal to alpha, where alpha denotes the prime coordinate. So this is our secondary coordinate, and this unprimed variable here denotes the let's say that initial or the unprimed coordinate system. So this is the transformation rule for a zero order tensor. So for a first order tensor, which is obviously a let's say a vector, we have, for example, something like a prime in the prime, and we already mentioned that it is q m I a m, where this was the transpose of the orthogonal tensor. So we transform this am to the prime coordinate using this orthogonal tensor here. So if we go to the second order tensor, then we have something like Tij is equal to Tmi, Qmi, Q and J Tmn. This is something that we discussed in the previous session. So we have the Q transpose times T times Q. And this was first written as, QIM, TMN, Q, and J, but this is the transpose, so this is written as QMI. This is something we already mentioned. All right, so what do we do for a third order tensor? So for a third order tensor, we follow the same pattern here. So if we have Sij, then we have Q, Mi, Q, and J, Q, R, K, S. So here we have Ijk, Ijk. They are three indices, so they appear on the left-hand side of the equation. So they shouldn't appear here. So it is MNR. So this is the third order tensor. And for the fourth order tensor, for example, then we have C, and these are all prime, sorry, I forgot. C prime I J K L is equal to Q M I Q J Q K, let's say P Q L Q, and this is C. So I, J, K, L, they are the pre-indices. They can't be repeated on the right-hand side. So we have M, N, oh, sorry, I think that I made a mistake here. So this is NJ. So this is P, K, and this is QL. So this becomes M, N, P, and then Q. So these are the transformation laws, and you can easily expand them to other, to higher order tensors. So let's get to the transformation rules. And I start by, let's say, the addition rule. All right. So the addition rule says that if you have, you can basically add two tensors which have the same order. So you cannot add a vector with a second order tensor. And I just wanted to say that from now on, we may call this as a vector, and I call this as a tensor. So whenever I say a tensor, so I mean a second order tensor. Otherwise, I will explicitly state it. So if you have, for example, if you have a vector, you cannot sum it with a second order tensor, or if you have a second order tensor, you cannot sum it with a fourth order tensor. So they have to be, they have to have the same order to be summed. All right. So let's say that if you have, for example, third order tensor like Wij here, and you can write easily from here that QMI in W prime IJK is equal to QMI QNJ and QRK WMNR. So here we can write W as the sum of, for example, two other tensors like T prime IJK plus S prime IJK is equal to. So I write each one explicitly. So I have QMI QNJ QRK TMNR plus SMI SNJ SRK SMNR. And remember here that in each term I am just writing I'm just repeating M, N, and R, so it doesn't violate the first agreement we made during the first session of the course here, because I did not put a dot here, so they are not there are two different terms here, so it doesn't violate the initial agreement we made. So this simply can be written as Q. Sorry, these are all Q. So QMI, Q and J, and QRK. So I can factor this out. I have T, M, and R plus S, M, and R, which is basically nothing but W, M, and R. So this is Q, M, I, Q, and J, Q, R, K, W, M, and R. So this is the same as what we got here. So the sum of two, let's say, third order tensor is another third order tensor. So the next, let's say the next rule is the multiplication rule. So it states that if you have, for example, AI as a vector, so AI is a vector, and if you have Tij is a tensor, or a second order tensor is a tensor, then you can say that the order of the product of these AI and Tj, or any other two tensors, or any other, tensors times each other. So if you have 3, 4, or more than that, then the order of the result of their product is equal to the number of their free indices. So for example, let me just write it here. So it can be proved that the product results order is equal to the number of free indices. So for example, if you have something like, let's say, AI, so examples, if you have AI, AJ, so there are two vectors, so finally you get Tij. Something like the dyadic product we had before. So the dyadic product of two tensors gives actually a second order tensor. Or if you have, for example, Tij TKL, so it gives you Cijkl, which is a fourth order tensor. Or for example, TIM-TMK gives you, since this is the dummy index n, so I and k are the free indices, so this becomes, for example, SIK, for example. And this gives a second order tensor. All right. So this can be easily proved for any kind of combination. But let's do it for example, a second order tensor, for example, and we do it again for a fourth order tensor. So for a second order tensor, let's say that you have for example, Tij is equal to AIAJ. Okay. So here we know that if we have A prime I, we can write it from this rule here, from the first order tensor rule. We can write it as QMIAM. I call it 1. And here I have A prime J here, A prime J, as Q, let's say, NJAN. And I wrote them like this because whenever we say, maybe it was better to state this later. Because, if you have Tij is equal to AIAJ, we assume that this happens here, then it is true for all coordinate system. So if Tij is equal to AIAJ, then it is true for all coordinate systems. So that's why we have t prime ij is equal to a prime I, a prime j. So that's why I wrote here a prime I is equal to qm I am and a prime j. All right, so I call this maybe 3. And if you plug in 1 and 2 in 3, so gives, so we have t prime ij is equal to q mi a m q and j a n, and this can be written as t prime ij is equal to q mi q and j a m a n, and this is nothing but tmn because these are two vectors, and t prime ij is equal to q mi q and j tmn. And this is nothing but the transformation of a second order tensor. So this is a second order tensor. These are the components of a second order tensor. So we made an assumption and we moved with this assumption, and finally we got the answer that we wanted. So the assumption we made is true. So let's do this for a third order tensor. So for a third order tensor, we assume that, for example, m prime ij, sorry, mijkl is equal to tij tkl, right? So if this is true, so this is true for all the coordinate systems. So we can copy this and paste it here. So if mijkl is equal to tijtkl, then it is true for all coordinate system. Then m prime ijkl is equal to t prime ij t prime kl, right? So from here, t prime ij and t prime ik, so I write t prime ij is equal to qmi q and j tmn, and I just got it from here. And I have t prime kl, which is equal to qrk qpl pl rk pl trp. So I have this 1 2 3 4 and 5, so maybe 5 6, and I call this 4. So substitute 5 and 6 in, let's say, in 4. So gives, if I have m prime ijk, so m prime ijkl is equal to, now I write this t prime ij here, q mi q and j t m mn q, now I write this qrk qpl trp, and I sort it like mi N, J, R, K, P, L, T, M, N, T, R, P. This is nothing but M, N, R, oh, sorry, M, N, R, P. And this is equal to M prime I, J, K, L is equal to Q, M, I, Q, N, J, Q, R, K, Q, P, L, M, N, R, P. And this is basically this fourth order transformation, as we already mentioned here. This is a fourth order transformation, so this gives us, a fourth order tensor. So the product of two second order tensor is a fourth order tensor. Now we move to the last rule, which is the quotient rule. And this rule actually states that if you have, let's say AI is a vector, and if Gij is a second order tensor, or simply a tensor, then you can conclude that AI is equal to Tij Bj. So from the product rule, then, therefore, or it's better to just write it in mathematical notation. So then Bi is a vector. So Bi is a vector, or Bj is a vector. We rated Bj because we wanted I to be a free index, but overall Bj or Bi doesn't make any difference. B, whatever you have, whatever subscript you put here, is a vector. And to prove this, so proof. So if we have, for example, AI is equal to Tij Bj. So if we assume that this is true, then, so if AI is equal to Tij Bj, then it is true in all coordinate systems. And we actually proved this, right, in the previous section, the multiplication. So we can write A prime I is equal to T prime I J B prime J. So I rewrite A prime I here. I call this, for example, star. So A prime is Q is equal to Q Mi MM AM, and T prime Ij is equal to Q Mi Q and J T M N. So if I transform this to their unprimed, so it becomes A I is equal to Q. So this is the transpose MI, MI, so it becomes IM, A prime M, and TMN becomes Q. This is MI, so we put we transpose it once more, becomes IM. This is NJ, so it becomes JN, and then we have this is IJ. This becomes TMN prime. So if I put this, so here is the star, made a mistake. So if I plug in, let's say 1 and 2, because I can control the numerators. So plug in 1 and 2 in star gives. So I have a prime. So a prime is here. Sorry, AI is here. So I have q I m a prime m is equal to tij, which is q I m q j n t prime m n. Finally, I have bj. Good. So now I have a prime m, and if a prime m, if we already mentioned this here, so if AI is equal to Ti j bj, then it is true for all coordinate system. Then from a prime I is equal to t prime ij b prime j. So I would call this black square. So a prime m. So from black square, a prime m is equal to, let's say, t prime m n b prime n, t prime m n b prime n, and I call this 3. So I plug in 3. So from 3, I have q I m instead of a prime an, a prime m. I write t prime mn b prime n is equal to q I m q j n t prime mn b j. I simply just copied this part here. Good. And now I can further simplify this by multiplying this by, this is QIM, right? So I have Q, let's say I have something like QMK. Oh no. So this can be written as QMI, QK, oh sorry, QIK. So we already proved this. So this is nothing but the transpose. So this is QIM, QIK. This is what I have here. And what is this? This is the transpose of this Q, and this is an orthogonal tensor. So this gives delta MK. So if I multiply both sides by QIK, I will have Q IK, Q IM, T prime MN, B prime N is equal to Q IK, Q IM, Q J N, T prime MN, B J. And maybe I can change this to red one. So we multiply it by QIK. And this is nothing but, so from, let's say, this rectangular here. So from rectangular, this is delta MK. And from here, we have delta MK. We already discussed this in the previous video, where we said that in tensorial, in matrix form, you have Q, this is Q transpose. This is Q is equal to the identity matrix, or here, since it is tensor algebra, it is identity tensor. So this is Q transpose Q. All right. So here it says that M is equal to K. So I leave it as M here. I don't have any K. So this becomes T prime mn b prime n is equal to Here m is equal to k, so I only have this m here, so I don't change it. I leave it as it is. T prime m n b j. So then I bring everything to one side. T prime m n b prime n minus q j n t prime m n b j is equal to 0. And I use the factorization, which we had in the I guess, maybe the first or the second session. So I factor out t prime mn. I have b prime n minus q j n b j is equal to 0. So this is not 0. This is a trivial solution. For the non-trivial solution, b prime n minus q n j n b j is equal to 0. Therefore, we have b prime n is equal to j q j n b j. So this is nothing but a first order or a vector transformation. Again, I bring your attention to here. So this shows that b I or bj or b is basically a vector, which implies bi is a vector, or bj or whatever, because it is a transformation of a vector. So it is just a first order tensor which is transformed into another coordinate. So it is a vector. We also have something else in the book, another example. So the book has stated that if you have Tij is equal toCijkl EKL. And if you recall this from your undergraduate course, we had sigma is equal to the stiffness matrix. So do not take this E as the stiffness matrix. So this implies the strain. We have epsilon. So we write it like sigma ij is equal to, and in continuum mechanics we show the compliance, this weird kind of notation that we show the the stiffness with C, despite the fact that it starts with S. So Cijkl, and instead of epsilon, we actually use Eij. Instead of sigma, we use, let's say, T. So it is the generalized Hooke's law. We already saw this in previous, previous sessions, and we already discussed this in a Jupyter notebook. So we have this stiffness showing by C, and also we have the inverse of the stiffness tensor. We call it compliance, and we show it with S. I don't know why, but this is the reason. So whenever you saw C, so it is the stiffness, and S is the compliance, and this is the most of the notation. This is the notation that most of the book follow, and that's it. So actually, this is nothing but the generalized Hooke's law. Generalized Hooke's law, and we're going to prove this. So here you have a third order tensor, you have a second order tensor, you have a fourth order tensor, and you have a second order tensor. So their multiplication actually gives you a second order tensor, which is the stress tensor. This is the stiffness tensor, and this is the strain tensor. All right, so we start from here, from T prime. So we state again that if Tij is equal to Cijkl EKL, So if this holds, actually, then it is true for all coordinate systems. All right, so then we can say that we have T prime ij is equal to Q m I Q and J T M N. And this can be written as, if we move from the prime to the unprime, T I J is equal to, we write Q I M Q J N, and this is T prime M N, right? So we also have, let me just move these in line. Right. So if we write the same for C prime I J K L, we had Q M I Q N J Q R K Q S L C M N R S, because these are the dummy indices, so they do not appear here on the left hand side. So if we move from the unprimed to the unprimed coordinate, then we have C prime, C I J K L is equal to Q I M Q J N Q K R Q L S C prime M N R S. So I call this 1 again, and this is 2. And I have my, let's say, my equation here as, let's say, star again. And I plug in 1 and 2 in star. So if we plug them, it gives. So maybe plugging in. All right, this gives 1 and 2 gives, let's say we have Tij is equal to Cijkl, this is EKL, so I had it here, right? So I can copy Tij from here, so it is QIM, so it is QIM QJN T prime MN, which is equal to, so C is QMI, so this is IMNJ, this is JN, this is KR, this is SL, so this becomes LS, C prime M, N, R, S, E, KL remains the same. So, and then we already mentioned from here that if Tij is equal to Cijkl, EKL, then it is true for all coordinate systems, but I forgot to write the transformed version, so I can maybe shift all these here a bit down. Perfect. So I can write T prime ij is equal to C prime ijkl E prime kl. Good. I call this as, again, the black square. So I can write from the black square by changing the indices, because I am not, because I want to change it to T prime mn. So T prime mn can be rewritten as, so from, sorry, from this black square, because we need to change the indices here. It is t prime ij, so I have to change it to t prime mn is equal to, so it was ij, so this becomes c prime mn rs e prime rs. I selected rs as it appears here, so I call this 3. So plug in 3, and let's say I call this let's say double star, maybe double star. So it gives let me see, okay, I have qim, so long expression, so I have to be careful. Jn, this is c prime mnrs e prime rs, and here I need to copy this, jn kr ls c prime mnrs e kl. Great. All right, so now I can get rid of this qim here if I make the same assumptions here, that if I have if I multiply this if I follow the same operation here, so I multiply it by qik, so again I bring it here, that if I have qm, let's say that I can't use k, so I use f, for example. So qm, so it becomes qmi if true. So if I just transpose this, so it becomes something like this and gives delta im. Great. So I multiply the above with let's say if. So I have qif here, and I have qif here. All right, so I have qif, q, again I bring it here, in qjn c prime mnrs e prime rs. Perfect. And on the other side I have qif, qim, qjm, qkr, qls, c prime mnrs ekl. I just multiplied qif with to this on both sides of this expression. So basically this gives delta fm, this gives delta fm, so it shows that f is equal to m, so I can substitute it with m, so it gives qjn. I don't have any f here, so I just keep it as it is, c prime mn rs e prime rs. I can even substitute this with f, but I just would like to stick to m. Sorry, qjn, yes, q, yeah, that is true, qjn, qkr, qls, c prime m mnrs ekl. Good. So again we follow, again we can multiply this by for example, if we have q n, let's say nz, I guess, and jz, so if I just, let's say that's q and j, so if I transpose this gn, so this is jz, so this becomes delta nz. Perfect. So I multiply both sides by Q J Z. Perfect. I have Q J Z here, and I have Q J Z here on both sides. So I multiply both sides of this expression with Q J Z. So I have Q J Z, Q J N, C prime M N R S, E prime R S is equal to QJZ, QJN, QKR, QLS, C prime, MNRS, EKL. Perfect. So I have here this as delta NZ. I have here this delta NZ. So N is equal to Z. Wherever I saw Z, I can substitute it with N or vice versa. I prefer to keep it as Z is equal to N. So C prime MN, MNRS. So instead of writing Z here, MZ, I prefer to write MN. So E prime RS is Q is equal to QR, QLS, C prime MNRS, EKL. So if I bring everything to one side, C prime MNRS, E prime RS minus Q KR QLS, C prime MNRS, EKL, KL is equal to 0. So I can factor out C prime MNRS. So I have E prime RS minus Q KR QLS EKL is equal to 0. For the non-trivial solution, this is supposed to be 0. So E prime RS minus Q KL QLS EKL is equal to 0. Therefore, E prime RS is equal to QKL QLS EKL, which is basically the transformation of E prime RS. So if you have it, so it is written as, sorry, I guess that I made a mistake here. So this is K. So this is KR. Okay, this is KR LSL. Okay, this is KR. And this is nothing but E prime RS is equal to, so if you transform this, this becomes, for example, something, if you write it by, let's say K, let's say M, for example, MR, then you have Q, so it becomes NS, and this is MN. And if we substitute this with Q, let's say, let me write it with MK and N with L, so this becomes KL. So it shows that this is a second order tensor transformation. So it shows that, therefore, KL is the component of, are the components of a second order tensor. And that's it.